Okay, so let us learn some terms as we continue in this chapter. So population versus sample. So population is whole sets of points that's measurable. Okay, and usually in the population, the mean is equals to mu, and the standard deviation is equals to a sigma. Now, population would have a lot of samples compared to a sample, which is a subset of the population that typically gets measured. So if in the population mean, you have mu and c. In the sample mean, it's just x plus or minus the standard deviation, s. Okay? Because the next lesson that we have is we're going to tackle about how they do samples, how they use the samples to represent the whole populations. This is very common, especially at this time of the election. How do they conduct survey and try to see that it is a representative of the whole population? So we go to this Gaussian curve. Okay. So in our last chapter, we discussed about random error and systematic error. So random error results in the scatter of results centered on the true value for repeated measurements of a single sample. Systematic errors, on the other hand, results in all measurements exhibit infinite difference from the true value. So if we're going to plot the number of occurrences or population of each measurement in a normal distribution, a Gaussian curve, this is how it looks like for the random error. Now for the systematic error, it can be higher or lower, okay, than the true results. So if we repeated the experiment many times, and if the error is purely, we could say, random, then the results tend to cluster symmetrically about the average value, which we can put here as the mean. Okay? And the more times the experiment is repeated, the more closely the results approach an ideal bell-shaped curve, which we call the Gaussian distribution or normal distribution. So if we're going to look at the mean, okay, as the value goes away from the mean, like this one, so plus standard deviation 68%, and then plus 2 standard deviation 95%, and plus 3 standard deviation, which is plus 3 standard deviation. So random error follows a Gaussian or normal distribution. So we are 95% certain that the true value falls within 2 times, okay, the significant, the standard deviation, which is infinite population. And if that happens, there's no systematic error. So for instance, we say that experimental data are normally distributed when replicate measurements exhibit the bell-shaped distribution. And in this Gaussian curve, okay, we say that we can find the probability with the use of the standard deviation. So in this case, we could say the most important part in a Gaussian distribution is the mean and the standard deviation. Okay, so if we're going to look for the formula for a Gaussian curve, we can say this is equals to C x minus mu over standard deviation. So x is the given value, mu here is the average, and sigma here is the standard deviation. Or if we want, so this is in terms of the population, but if you want to do it in terms of the sample, so this is just the given value minus the average over the standard deviation. So here in this slide, you're given here an example of a set of data. Now, to give you an idea what it is, A manufacturer tested the lifetime of 4,768 bulbs. Now the bar graphs here show the number of bulbs with a lifetime in each 20-hour interval. Okay, so this is where the data came from. So as you're going to look at it, there are two parameters that characterize the light bulbs. And this is the mean and the standard deviation. Okay, so if she plans to sell 1,000,000 bulbs, how many extra bulbs should be kept available? So we could say this is a result of 4,768 bulbs. Now, the manufacturer offers free bulbs for those that has 600 hours, less than 600 hours. So what does it mean? Anything that is less than here, the manufacturer is willing to replace free of charge. Now, if you sell 1,000,000, how many will have a lifetime that is less than 600 hours? So that's how this problem represent. So what do we do here? We're going to solve this using this formula. So following that thing, so you have what? 600 minus 845.2 divided by 94.2. Okay? So if we have this calculation, what do we get? Okay? What do we get if we have this calculation? So if we're going to look at this, I think the main problem that we have here is listed here in the later slide. So if we're going to look at the way that we're going to solve this, okay? So you're going to have the one that I have listed there, the 600 minus the average, which is 845.2 divided by 94.2. And if you're going to do it, you're going to get 2.60. Okay, so what does this C equals to 2.60 represent? So if we're going to look at here, 2.60 refers to the area that you have here, and that's the area or the population that represents less than 600 hours. So to answer the question that you have there, you will be using a table like this. So all you need to do is whatever the value that you have, so whether it's positive or negative, it's the same. So it represents here. So how much does this represent? So if you're going to look at this one, so you could say half of the population are here and the other half are here. So if you're going to look at the area that you have there, that 0.4953, so that represents the area on this one. So if you're going to get that thing, so you're going to add 0.5 minus 0.453. So you will get there 0.5 minus 0.4953, around this value. So that represents the fraction that has less than 600 hours lifetime. Okay, so if you're going to get the the percentage of that, so you have what, 1 million, 1 times 10 to the 6. So all you need to do is you multiply 0.0047 to that value. And you will get 4,700. So that 4,700, that's the bulbs that you need to produce, because that's the number of population that will have less than 600 hours. Okay, so you don't need to do the whole 1,000. All you need to do is do some subset. Okay, a representative sample, and from that alone you can have an idea how many bulbs you need to prepare. Now there are other questions that you can be asked here. Okay, so this table, you should have this handy. You can have a question like, what fractions of bulb is expressed to have a lifetime between 900 and 1,000 hours? So if you're going to look at this problem, you go to the distribution curve, or the Gaussian curve. So you could say how much of this will have a lifetime between 900 to 1,000 hours. And you can always do the C equals to 900 minus 845.2 divided by 94.2, and then the C equals to 1,000 minus 845.2 over 94.2. So if you have that, you will get a value of this 0.58, let's say 17, or we could just say around 0.58 and 1.64. Now, how are we going to get the value here? So I can just put here, look at the table. So you're going to look with 0.58, which unfortunately is not given. So maybe we're going to use the 6 here, the 0.6. So you're going to use the 0.2258. Okay. And you're going to subtract it with whatever is the corresponding 1.64, which I think is not given. So you're going to use here 0.4452. So this represents, okay, the area under that curve. And what you're going to do here, if you're going to get the difference here, so you're going to get 0.2194. So this represents the fraction that has this lifetime. And if you're going to calculate that one, so in a million, 1 times 10 to the 6, you just multiply it with 2194. So what do you get there? So this is the amount. One, two, three, four, five. So you have 219,400 bulbs. That is between this thing. Now there's a shortcut for this. Okay, you can do is using Excel. So the way that you're going to do it here, at least here, it will going to give you the exact value. So remember, we use a 0.6 and a 1.6, if I'm not mistaken, from the table that we have. So if you want the real one, so you can try to do it. So you could see it's really 23%. So what we have here is only 22%. So this is the way to check if you get it correctly. Okay, so I would suggest do it. So this is the how to do the C-test. So you can use this in the surveys that you have in the election.